Hi, everybody. So this is going to be our first review video for the AP test. And what we're going to try to do in this video is to review some of the major ideas that occur in units 1, 2, and 3 of AP Calculus. There's going to be a lot of information in this video. And the idea is that if you take really good notes and you keep track of these notes, then since we're going to be reviewing for the AP test, this is not only a great study tool, but this could also be used during your take-home AP test this year. You can kind of have these next to you while you're taking the test in case you need to look something up really quick. I also want to highly recommend, however, that you don't come to depend on looking up every single question. You definitely will not finish the problems and you will not finish the test in the allotted amount of time if you have to look up every single question. So part of the reason we've created this review and these review materials is so that you can really learn it and review it now so you don't have to look up every little thing when you're taking the test. So let's go ahead and get started. If you think way back to the beginning of the school year, the first thing we started with this school year was actually the idea of limits. So we're going to take a second and we're going to review how to determine a limit from a graph, determine a limit from a table, determine limits using algebra, and then what we learned later on is you can actually find limits using something called L'Hopital's rule as well. So let's find a limit from a graph. If we want to find a limit, there are three different types of limits we learned about. There's the limit as you approach your number from the left. And I know that this is from the left because of the little negative there above the number that I'm approaching. There's the limit as I approach my number from the right. And there's the limit as I approach the number from both sides, which we call a two-sided limit. So in order to find the limit as you approach -3 from the left, we would find the number -3 on the graph, and from the left of there, so if you're starting from -3, move to the left, and then head back towards your number. If I follow this graph, starting from the left side, heading towards where x is -3, I can see that the y value that I'm approaching is the number 6. Now, it doesn't matter that there's an open circle there. That doesn't affect the way we do a limit. We're just asking what y value are you getting closer to? If I wanted to find the limit as I approach -3 from the right, what I'm really asking is if I'm standing on the -3, move to the right, and then go back towards the number. So as I approach -3 from the right, my value would be 2. Last but not least, let's talk about a two-sided limit. So when there's no little plus and there's no little minus, this is what we call a two-sided limit. In order for a two-sided limit to exist, both sides have to agree. Now, since the 6 and the 2 are not equal, we would say that this two-sided limit does not exist. And if we were ever asked to justify our answer, we would say because the limit as x approaches -3 from the left of h of x does not equal the limit as x approaches -3 from the right of h of x. So we would just write down these two notations and just put does not equal in between. Now, one of the other things we learned is that we can find limits from a table. So this does not exist because this does not equal. All right, so another thing we learned is we can find limits from a table. Now, this gets a little bit trickier for some reason. I think it's because we're kind of looking at numbers now instead of using our eyes to just look at what's happening. So if I wanted to, for example, in this table, look at what's happening as I approach the number 7 from the left. If you imagine a number line, the numbers to the left of the number 7 would be these x values over here. So this is the part of the table that I'm going to look at as I'm approaching 7 from the left. Now, if I follow those numbers closer to 7, I can see that the number is approaching -1.925. We're always going to go to 3 decimal places here. So I would say -1.925. If I want to figure out what's happening as I approach 7 from the right, if you imagine a number line, that would be the right side of the table. So that's going to be these numbers right here. And as I approach the number 7, which is in the middle, these numbers are getting closer to -1.92, and then the 8 is big enough to bump up the 4. So -1.925 again. And again, for my two-sided limit, I'm comparing these two values. And if they're the same, then my two-sided limit would just be whatever I have, so -1.925. Now, I will say the common mistake both here and here is that students tend to get really bogged down in where the actual function value is. So the common mistake is that students get confused and they think that since the y value, the output when x is 7, is undefined, that the limit is undefined. So the common mistake would be thinking the function value or output affects the limit value. I cannot even tell you how many times I've had a student tell me that these limits are undefined because this says undefined. What we need to remember is that for limits, where the actual closed circle is or whether the closed circle exists at all, it does not matter. It's just what are you getting closer to. So in a similar way, a lot of students tell me that the limit here from the left side is 2 because that's where the closed circle is. But we don't care. What we're doing is we're saying get closer to this spot from the left side. What are you getting closer to as far as your y value goes? We don't care what happens about the actual function value, the closed circle or not. So be really careful about that. Don't let that trip you up. All right, one of the other things we learned is that it is possible to find a limit using algebra. So the number one rule for finding limits using algebra is that you should try to substitute the x value. So if you do have an equation, you should try to substitute the x value into the equation. And if you substitute and you get an answer like 3/7, then that's the value of your limit. If substitution gives you one of these kind of different cases, then we have different ways to do the problem. So if substitution gives you 0/0 or infinity/infinity, we called these indeterminate forms. And in that case, we would use L'Hopital's rule. Which we're actually going to review in the following part of the notes. If substitution gives you 0 divided by a number, well, 0 divided by a number is just 0. So the answer would just be 0. If the substitution gives you the number divided by 0, you cannot divide by 0. So that's your first clue that something is wrong here. It's not 0 divided by 0, so it's not indeterminate. It's a number divided by 0. When that happens, you need to either imagine the graph, which we'll talk about in a second. You either need to imagine the graph, it's going to have an asymptote, or you need to choose a number a little bit to the left and choose a number a little bit to the right and see what happens. So let's talk about these graphs really quick. So if you have a number divided by 0, it's because you have a rational function. So one of the things I want to remind you of is that if you have a positive numerator, a negative numerator, and then if you have an odd power or an even power, can tell you what's happening with the graph. So here's what I mean. If you have a positive numerator like 4 divided by something like x minus 2 to an odd power like 3, so positive divided by an odd power, then your graph is always going to be an asymptote at 2, and then because it's an odd power and a positive, the two sides of the asymptote go like this. In which case, your limit would be does not exist because the two sides don't agree. If you have a positive numerator divided by an even power on the bottom, like to the fourth power, then when you look at your graph, your asymptote would be at the number 2, but both sides would go up. If you have a negative numerator, like -4, divided by an odd power, then it's the same idea. So at the number 2, only this side goes up and this side goes down, which is kind of the flip-flop of this guy. And if you have a negative numerator, like -4, and you have an even power on the bottom, like a fourth power, then near that asymptote, your both sides are going to go down. So when your power is even, both sides go the same way. When your power is odd, both sides go opposite ways. And then the top, the numerator, tells you which side goes up and which side goes down. So if that happens, if you get a number divided by 0, since you cannot divide by 0, you need to, there must be an asymptote. So you need to kind of visualize the graph of what's happening here. If both sides are going the same direction near that asymptote, then that's going to be your limit. So your limit would be positive or negative infinity. And if they're going opposite directions, your limit does not exist. If you end up with infinity divided by a number, the answer is just infinity. Because if you have infinity pizzas to share with 4 of your friends, everybody gets a lot of pizza. And if you have a number divided by infinity, the answer is 0. Because if you have 4 pizzas to share with infinity of your friends, everybody gets no pizza. Now let's go ahead and review L'Hopital's rule. So we know that if we get one of these indeterminate forms, if we get 0 over 0, or if we get infinity over infinity, we're going to use L'Hopital's rule. So here are some things you need to know about applying L'Hopital's rule. The first thing is that on the AP test, you must state the indeterminate form before you can apply it. So you must say whether it was 0 over 0 or infinity over infinity and say that that is an indeterminate form. You must state that you are using L'Hopital's rule to solve. So after you say this is a limit whose form is indeterminate, it's 0 over 0, you have to say I'm applying L'Hopital's rule. After you say those two things, to actually use L'Hopital's rule, you should take the derivative of both the top and the bottom separately. So you're not doing quotient rule here. You're just doing the derivative of the top and the derivative of the bottom and substitute again. So after you do the derivative, plug in your number again. Now, if you still get an indeterminate form, you can apply L'Hopital's rule for a second time. So you could say, I still have 0 over 0. I'm doing L'Hopital's rule again. If you don't have an indeterminate form, then whatever you get by substituting is the value of your limit. Okay, let's connect now limits and asymptotes. So it turns out there's a very strong connection between limits and asymptotes. If we're talking about horizontal asymptotes, we can find a horizontal asymptote using limits. So if I ever say, where are the horizontal asymptotes of this function? You can find the limit as x goes to infinity and the limit as x goes to negative infinity to find those things. So if you find the limit as x goes to infinity and you get 7, then that is a horizontal asymptote. If you find the limit as x goes to negative infinity and you get 7, that's a horizontal asymptote. If you find these limits and you get infinity or negative infinity as your final answer, there is no horizontal asymptote. So if you know, on the other hand, that the limit as x goes to infinity of f of x is 7, then the line y equals 7 must be a horizontal asymptote. So one of the things that we are often asked on the AP test is, if you know this limit, which of the following things can you say are true? Now the same thing applies to x approaching negative infinity. So let's say that this said negative infinity here and you got 7. The line y equals 7 would still be a horizontal asymptote. As far as vertical asymptotes go, You can find vertical asymptotes by looking for what makes a function undefined. So if you find a limit as you're approaching some number, and you get either positive or negative infinity, that must be a vertical asymptote. Because what you're saying here is that when you got close to that specific x value, the y values of the graph went up towards positive infinity or down towards negative infinity. Now, at the same token, if you say, for example, the limit as x approaches 7 of f of x is infinity, then the line x equals 7 must be a vertical asymptote of this graph. So it's really important to kind of understand those connections. When in doubt, my suggestion for both of these would be to sketch a picture so that you can visualize what's happening here. It is always easier to visualize what's happening if you actually draw it in front of you. Okay. Continuity. Now, the reason we're talking about continuity next is that in order to figure out whether a function is continuous or not, it really depended on limits to do that. So this was the next topic that we really talked about because it was an application of limits. It was how do we use limits to answer questions. So the definition of continuity is that a function is connected. That's kind of how I would say it to somebody who didn't know the technical definition. However, the technical definition here is really important because as you're going to see in some FRQs, we are asked to determine whether a function is continuous or not and justify our answer. So the technical definition has three parts. The limit as x approaches your number from the left, the limit as x approaches your number from the right, and the actual function value where you plug in your number. All three of those things must be equal in order to prove that your function is continuous. So if you're ever asked to prove it, you need to find this limit, find the function value, and show that they're all the same. Now, when we talk about continuity, there are different types of discontinuities. So the first type of discontinuity is a jump. The second type of discontinuity is what we call removable. The third type is what we call infinite. And the last type is what we call oscillating. Now, we don't usually see oscillating come up all that often, so I'm really going to spend my time focused on jump, removable, and infinite. A jump discontinuity is what happens when the limit as you approach your number from the left does not equal the limit from the right. So if you envision a graph, if we pick a number, the limit from the left is different than the limit from the right. There's an actual jump in the graph. You are most likely going to see a jump discontinuity when it's a piecewise function. So when we have a piecewise function, that's kind of one of the times we really want to watch out for a jump discontinuity. A removable discontinuity means that the limit as you approach your number from both the left and the right, so you'll notice I'm not putting a little plus sign, does not equal the function value. So the left and the right agree, but when you get there, there's an actual hole in the graph. So it's going to look something like this. Now you're likely to have this either when there's a piecewise function or when there's a rational function where a factor of the numerator cancels a factor of the denominator. So something like this, x plus 2 times x plus 3 divided by x plus 2. Since the 2's cancel, you're going to have a removable discontinuity at -2. An infinite discontinuity would be when the limit as x approaches your number from the left is either infinity or -infinity, and same thing for the right. So you're looking for an asymptote. It's really a situation where the graph is going towards infinity instead of approaching a value. And this is most likely going to happen again with a rational function, but this is going to be a case where a factor doesn't cancel. So if you have 1 over x plus 5 and the x plus 5 doesn't cancel, that's going to give you an infinite discontinuity. It's going to give you an asymptote. Oscillating only happens with very specific and particular types of sinusoidal functions, so sine, cosine, stuff like that. So we don't really see that come up that often. Now, the idea of continuous versus not continuous can be determined by obviously looking at a graph. Just use your eyes. Is it ever not connected? But we can also figure this out by looking at algebra and manipulating a problem. So, for example, in this one it says, determine whether your function is continuous or not at x equals 3. Now, you're always going to be determining continuity at a specific number. So you're not going to ever have to worry about just, is it continuous everywhere? Because you'd have to be able to check every single value. They're usually going to ask you about a specific number. And in this case, they're asking you about the number x equals 3 because that is the place of the piecewise function where the piecewise function has something changing or a potential disconnection. Now, in order to figure this out, we need to show 3 things. We need to find the limit as x approaches 3 from the left. We need to find the limit as x approaches 3 from the right. And we need to find k of 3. Because by finding all 3 of those things, we can actually see if they're equal and therefore see if the function is continuous or not. So we want to know, are these things equal? So I'm going to write an equal sign with a little question mark above there. Well, let's go ahead and work on the limit as I approach 3 from the left and the limit as I approach 3 from the right. Now I'm saying and because we're actually going to do both of these things the same way. If I'm reading this correctly, it means that this top part of the equation applies to all of the numbers that are not equal to 3. Now, if I'm approaching 3, whether it's from the left or the right, then I'm not equal to 3. I'm not standing on the 3, I'm just getting close. So for both the limit as I approach 3 from the left and for the limit as I approach 3 from the right, I'm going to use the top part of this equation. Now, in order to figure this out, my first thing I'm going to do is I'm going to try plugging in the number 3. If I plug in the number 3, then on the top I get 0 and on the bottom I get 0. But one of the things that I noticed right away is that I can actually factor the numerator here. The numerator factors to be x plus 3 times x minus 3, which means that the x minus 3's cancel. So all I'm left with is x plus 3. If I try plugging the 3 into the factored version and the one that I simplified, I just get 3 plus 3, which makes 6. And I'm going to get 6 for both of these because both of those are places where I'm not equal to 3. I'm just getting close to 3. Now, in order to figure out k of 3, so what happens when I actually am equal to 3, I'm going to use the bottom part of this piecewise function because that's the place where I'm actually equal to 3, in which case I also get 6. Since 6 does equal 6, which does equal 6, we would say k of x is continuous at x equals 3. Now, one last piece of the puzzle here is that we can actually take a function with a missing value and choose just the right value that will make that function continuous. So these directions say find the value of c that will make the following function continuous at x equals 5. So if I want to do this, then that means that I want the limit as x approaches 5 from the left to be equal to the limit as x approaches 5 from the right, and I want both of those to be equal to f of 5. Now, to do that, to find these limits and stuff, I'm going to take the number 5 and plug it in. So to find the limit as x approaches 5 from the left, I'm going to take the number 5 and plug it in for all of the x's. That gives me 25c plus 4 times 5 is 20. Now, in order to find the limit as x approaches 5 from the right, I'm going to take the number 5, because this is the number is bigger than 5, and plug it in for all of the x's, which gives me 125 minus 5c. To find f of 5, I'm still going to use the bottom function here, which I've already got here, so I'm not going to do that again. It's going to give me the same answer. And this is just an equation that I can solve. So to solve this, I would add the 5c to the other side, so I would get 30c. I would subtract the 20, so I would have 105. And then I would divide. So c equals 105 over 30. Now you can reduce this. You could divide everything by 5, which gives you 21 over 6, and you could divide everything by 3, which gives you 7 over 2. Keep in mind that on the AP test, you will have a calculator, so if you need to check your arithmetic, please feel free to do so. For our next topic, and like I said, I know this is a longer video, there's a lot to review here. For our next topic, we're just going to review some derivative rules. Now, I'm going to be honest, for a lot of these rules, I just wrote them down for you. So you can go back and review trig rules, exponential and logarithmic functions, inverse trig functions on your own. Those are just some rules that it might be nice to have handy when it comes to time to take the AP test. There are a few rules I want to go over together. So the first rule I want to go over together is the power rule. I just want to remind you that the power rule for derivatives just says drop it, which gives you 24 over 3, which is 8, x to the, and then subtract 1, which gives you negative 1/3. I also want to remind you that negative 1/3 really means drop it to the bottom, and that a 1/3 power really means a cube root. Now, on the AP test, you don't need to rewrite it that way. You can just leave this as your answer. However, if you're given a problem that looks like this, it's probably going to be easier to rewrite it back this way in order to find derivatives. So I just wanted to review the different forms of writing equivalent expressions here, so that if you need to go back and forth between the different forms, you can do so fluidly in order to make your life easier when it comes to finding derivatives and antiderivatives. There are a couple other kind of big rules that I want to remember. And if you're going to ask me to bet on it, I'm going to guess this is how you're going to see the problems if they ask you any about derivatives on the AP test, because this doesn't require you to memorize any other rules. It's just about knowing the basic operations. So let's review product rule first. Product rule is the rule that we use when we have two functions that are being multiplied together, f of x and g of x. In order to do product rule, to take the derivative, you would copy the first equation and then take the derivative of the second equation. Sorry, second factor, I guess. Plus, then you would copy the second one and then take the derivative of the first one. Now, we also learned quotient rule. Quotient rule is the rule that we use when you have a function divided by another function. And so to do this, you would do low, which is g of x, d high, so take the derivative of the top, minus high, so f of x, d low, so g prime, and then low squared goes down below. Now, we did sing a song for this, so we said that this was low d high minus high d low, and low squared goes down below, which helps us remember the formula. I expect that if you were going to do these problems on the AP test, it would probably look something like this, and I think you're going to see some problems where you have to really understand these rules in the FRQ questions you're going to try. Now, the last rule you kind of need to know is chain rule. And chain rule is just explaining to us how we take the derivative when we have a function nested inside of another function. So the way we do this is we take the derivative of the outside and we leave the inside alone. So this is still just regular g of x. Then we multiply by the derivative of the inside, so g prime of x. Okay, that's some basic derivative rules. Now here's some vocabulary that goes along with derivatives. So the first vocabulary term that we need to know is the term average rate of change. Average rate of change is also known as the slope of the secant line. The formula for average rate of change is just regular old slope. So f of b minus f of a all over b minus a. Instantaneous rate of change is also known as the slope of the tangent line, or what we usually call it is the derivative of the function. Now, to find your instantaneous rate of change, you need to use all of those derivative rules that we just reviewed. So this is going to be really kind of where those derivative rules, one of the applications is to find the slope of the instantaneous rate of change. Sorry, the instantaneous rate of change, the slope of the tangent line. And the reason I want to put this one on here, even though it's kind of off topic, average value, is that average value is often confused with average rate of change. But average value would be something like the average temperature, in which case you would actually do 1 over b minus a times the integral from a to b of your function. So I just want to remind you that average value is a little different than average rate of change. Now, one of the things you're often asked is write the equation of a secant line or write the equation of a tangent line. In order to write the equation of a secant line, you always want to organize your work as this. You need a point, need a slope, you write your line. So if the directions say write the equation of the line that is secant to the curve f of x equals x squared over the interval from 3 to 4, the first thing you would do is you would list your point. Now, as a reminder, in this question, both of these numbers are x values, not an ordered pair. It's not an x comma y, it's two x values. You can use either one of those as your starting point. I'm going to use the 3 because it's first. To find your y, you would just take the 3 and plug it in to the original equation, which gives you 9. Now, to find your slope, you would do this slope right here, regular old slope. It's the slope of the secant line. So I would do f of 4 minus f of 3 all over 4 minus 3. Now, f of 4 means take the number 4 and plug it in. So I would get 16 minus f of 3 means plug it in, so 9 all over 1, which gives me 7. And then last but not least, I would write my equation of my line. So y minus my y value, which is 9, equals my slope, which is 7, parentheses x minus my x value, which is 3, from my ordered pair. Now, if I want to write the equation of a tangent line, it's going to be a very similar organization. We still need a point, we still need a slope, and then we write our equation. The only difference is how we find our slope. So for our point, we're still going to take an x and plug it into the original to get a y. To get our slope, however, we're going to take the derivative. So the derivative of x squared would be 2x. Then I would plug in my desired x value. So plug in the number 3. Last but not least, write the equation of my tangent line. So y minus 9 equals my 6, which is my slope, parentheses x minus 3, which is my x. Once we learned about derivatives, we learned about something called differentiability. In order for a function to be differentiable, it means the derivative exists. So if the derivative is the slope at a single point, it's the instantaneous rate of change, then there are going to be times when it's impossible to find that slope. In order for a function to be differentiable, it must be continuous. So a function must be continuous in order to be differentiable, which means if I ever ask you to determine whether differentiable, If I ever ask you to determine whether a function's differentiable amount or not, we always check to see if it's continuous or not first. So this is like level 1 clearance, and then this is level 2 clearance. You can't be differentiable if you're not continuous. Now, there are different types of locations that are not differentiable. We've got corners, we've got cusps, we've got vertical tangent lines, and we've got discontinuities. So, discontinuity. A corner is always going to occur or usually going to occur in an absolute value function. So a corner looks something like this. You want to watch for an absolute value function. You want to watch for a piecewise function. A cusp is normally going to look something like this. And for that, you want to watch for an exponential function. Or not an exponential, a polynomial, I guess, or a power. I apologize. That is rational. Something like this, x to the 2/3 power. A vertical tangent line is going to look something like this. And again, you want to look for a power that is rational. Something like this to the 1/3. The only difference is that this is the powers that are even in the numerator, and this is the powers that are odd in the numerator. That's the difference between a cusp and a vertical tangent line. Now, discontinuities, well, we have an entire section about discontinuities. So this idea of if you have a discontinuity, you're not differentiable, you can refer back to this portion of your notes where we review discontinuities to see when you should be concerned about a discontinuity. Now, we can determine whether a function is differentiable or not using algebra. So in order to figure this out, we would start by checking to see if we are continuous or not. Now I'm going to check to see if I'm continuous or not at 0, because 0 is kind of the breaking point of this function. So if I take the number 0 and I plug it in here, I get -3. And if I take the number 0 and I plug it in here, I get -3. Because those agree, I am continuous. So I would say the limit as x approaches -3 from the left, x approaches 0 from the left is -3. The limit as x approaches 0 from the right is -3, and f of 0 is -3. Therefore, I'm continuous. Now, if I want to see if I'm differentiable, I'm going to take the derivative and do the same thing. So the derivative of my function here would be 3 and would be 2x plus 4. Now I shouldn't have put an equal to there. This is only for when x is greater than 0, and this is for when x is less than 0. I'm not going to put the equal to in because right now I don't know if my derivative exists and includes the 0 or doesn't. In order to determine that, I'm going to take the number 0 and plug it in here, which I get 3. And I'm going to take the number 0 and plug it in here, which means I get 4. Since those do not agree, I am not differentiable because the limit as x approaches 0 from the left of my derivative does not equal the limit as x approaches 0 from the right of my derivative. So we checked our limits for the original to verify the continuity, and we checked our limits for our derivative to verify the differentiability or not. Now, there are some functions you should be aware of, and we kind of listed them up here already, so I'm not going to rewrite them, but you should watch out for absolute value functions, piecewise functions, power, rational exponents, so if they're even or odd numerators, and those are all going to tell you what types of non-differentiable spots we have. Okay. All right, let's take a look at the last thing in our notes. And I know this is a very long video, and I hope you're watching it in pieces, but it's a lot to review. So the last things in our notes are going to be the intermediate value theorem and the mean value theorem. And these are kind of the big two theorems that you're going to need to be familiar with for the AP test. There is a third theorem, but we don't ever have to really write it this way. So the intermediate value theorem says that if f of x is continuous, and the y value that you're trying to guarantee is between f of b and f of a, the two y values at the endpoints. So I'm continuous between these x's, and my y value is between the y values of the endpoints. Then there must be an x value, which we usually call c, between a and b, such that the y value, when I plug in c, is equal to my desired y value. What this is basically a complex way of saying is, if we think back to when we did the speedometer experiment in class, we looked at the speedometer, we said, okay, you can't jump from 20 to 40 miles per hour without crossing through 30. So if you know what the y value is at the beginning, and you know what the y value is at the end, you can promise all the y values that are in between as long as your function's continuous. Now, we're going to know that we should use this when a question asks whether you can guarantee that a function has a particular y value. And an example of a prompt from an actual AP test that does that looks like this. Explain why there must be a value r between 1 and 3 such that h of r equals -5. So we're trying to show that the y value is -5. Here are the steps that you follow. Number 1, make sure your function's continuous. If you want to know whether you have a discontinuity, see the functions that have issues that are listed under discontinuities earlier in these notes. Then find f of b and find f of a. So find the y values at the endpoints. Check to see if the y value that you are trying to guarantee, which in this problem would be the -5, is between those two numbers, the ones you just found. Then, if it is, you can say, since f of x is continuous on that interval, and the y value, whatever one it said, in this case it'd be -5, is between f of b and f of a, then there must be an x value between a and b such that f of c equals the y value. In this case, you would say then there must be an r between 1 and 3 such that h of r is equal to -5. Now, the mean value theorem, which is our second big theorem, has to do with derivatives. So for this theorem, the first thing is f of x has to be continuous. Because if you're not continuous, your derivative doesn't exist. And f of x has to be differentiable, because we can't answer questions about a derivative unless our derivative actually exists. So we have to be connected and we have to be differentiable. Then there must be a value between your endpoints such that, and this is a formula that you need to write down, such that f prime of c, so the derivative at that x, is equal to f of b minus f of a all over b minus a. So in other words, if you think back to what these things are, the average rate of change is equal to the instantaneous rate of change. Now, you're going to use this when a question asks whether you can guarantee that a given function has a particular slope or derivative. So an example from an actual AP test would be explain why there must be a value c between 1 and 3 such that h prime of c equals -5. So here we're being asked to guarantee a specific derivative. Here are the steps you would follow. Number 1, make sure your function is continuous and differentiable. And if you want to think back to how to do that, look back earlier in our notes where we talked about what makes a function continuous and what makes a function differentiable. Then find the average rate of change. So find this guy. Then find the derivative. Find this guy. And finally, set them equal and solve for your x. That x that you find is the c value. So whatever x you get is the c value where that happens. All right, I know this is a lot of information. I appreciate you guys taking notes, and let's kick off this AP review on the right foot and make sure that we've got this under control.